All right, so here we are for Physics 1. Now, just to look at our Moodle page, this will be our home here for this term. This is where I post, news and bits and pieces. This is where you can come to ask a question about homework. This is the day-by-day schedule for the course. Notice that there's a class number and then a topic, and then here there's dates. For our section, it'll be the first number that you're interested in. I'm teaching more than one section of this course. So September 8th today is pressure, and then next class, September 10th, will be buoyancy, and so on and so on. Notice that the exams are already scheduled, so we've got our first exam, our first class test on October the 6th, and then our next one is on November 5th. There may be, depending on time, a third exam on December 3rd. So there'll maybe do like up to 3 class tests. Then, of course, there'll be a final exam, which has already been scheduled. More on those exams a little later. So next on the Moodle page, the syllabus. So basically what you want to know here is marks and things like that. So we are going to be meeting like this for the whole term. Each class, I'll talk a little bit, do a few examples. Then there'll be an opportunity for you to do an example. We'll discuss the answer together, and then hopefully I'll be able to set up breakouts where you guys will work together on some problems in class. The idea is that we can hopefully finish all the homework problems by the end of our time together. So all the materials will be provided through the Moodle page just as PDF, so that saves you money. There are labs with the course, and your lab instructor will be in touch with you about that. That's 20% of your final mark. This says 2 tests. There may be 3, but it's going to add up to 40% in total. There'll be a final evaluation, which is a final exam. There are assignment sets, which are individual work for 10%, and then in-class work will largely be quizzes. That'll be the final 10%. There's the A's, B's, and C's. Basically, this says, you have to complete all the labs. And if you think you're going to miss a lab, you should get in touch with your lab instructor. Oh, actually, hold on, they're not scheduled anymore. So yeah, you just have to complete them all. I think you're doing them at home. You have to get a little apparatus set, but your lab instructor will give you details on that. For the tests, you actually are going to be writing them at home. So I'm going to put the questions up, and you're going to do them and scan them and submit them. This, of course, is not ideal, and you should know that we do check on things as much as we can. So it's best just to be honest and, do the tests in the spirit that they're intended, which is that it's closed book and individual work. Okay, dates and deadlines are here. Policies basically say be nice and don't cheat. And then this just says that if you're struggling, I may call on something known as the early alert system, where I'll sort of, if I see, for instance, the work's not being done, you've missed a few assignments or something like that, I'll just get somebody to give you a call, and they can, help activate rather all the resources that we have here for student support, because everybody wants you to be successful. And that's what that's about. So with your permission, if I notice, something that is concerning me about how you're doing in the course, I may activate that system just to support you. Okay, next formula page. So these are the formulas for the course. It's in your class notes. It'll be on all the tests as well. Some people like to have a textbook for the course, so I've given this huge PDF here, which is OpenStack, so it's free for everybody. And if you want to do some background reading, it's there for you. I will not be referring to this text at all. So it's entirely just there for you if you have some time and want to do an extra reading. All the topics that we cover are basically there. So here's the link for Big Blue Button, which will hopefully work, enable us to meet online every class. If it fails, I'll have a Zoom membership as a backup, and I'll email you and give you the link to the Zoom meeting if it turns out that the Quantly site goes down for some reason. Okay, so each and every class there will be a pre-lecture video to watch, and you will use that video to fill in some notes. And the idea is that you're just going to go through the basics before class so that I don't have to do that, so we can leap straight into slightly harder problems and then you actually working on the homework under my supervision. That's the way that the class will work. What is the homework? Well, it's given in this extra practice list, which is there for every class. After you do that extra practice list, for mastery, there is an assignment for you to do. And these assignments, you have about 2 weeks for them. I realize I have to set the due dates here. Well, let's just do that right now. So edit settings. So today being the 8th, we will give you, oh, we have to change the year, don't we? Ha ha ha. Okay, so we'll change the year. So 8 plus 14 is 22. So there you go. It's due on the 22nd of September. Now, the intent here is that you get it right and you figure it out. So I give you lots of attempts, and there's no penalty for using multiple attempts. Everybody has the same question stub, but your numbers are different, so your answers will be different. So you can get together and talk about how to do it, but your friend's answer and your answer numerically will be slightly different. Okay, so view these assignments, please, as an opportunity to make sure you understand everything. And if you're not getting the answer right, then talk to me about it. This video conference can also be used for office hour consultations as well, so we can meet there and talk about it, or we can use Zoom. So do avail yourself of that opportunity. Office hours will generally be after class, each class, for about an hour, or for however long I guess people want to come and talk to me. Okay, so that's class 1. Class 2 is already ready here for you. There's a pre-lecture video, and the notes are there. And then some extra practice exercises. Now you may notice on my page some things that are hidden from students. These quizzes are here, and these are things that I will kind of pull out of the hat now and then and say, okay, you got 15 minutes to work on this. When we were meeting face-to-face, I had students do it by themselves and then do it again in a group. I may try and get that working for us here using breakout sessions, but that sort of will be a work in progress. So that's a quick look at the Moodle page and how things are going to go for us this term, sort of, how the class will be structured. And so the next thing for us to do is to actually go into our notes, and as promised, each and every day I will do a couple of examples with you. And so let's please open up Class 1 notes. So I guess some of you will have it on paper, some of you will have it on your iPad, and we'll turn to page 14, where I'll do a quick example or two with you. All right, so let's start with our notes for today's class then. So here's our workbook. And the workbook is sort of notes templates, and there's sort of areas where you fill in things. Now, I would do a few demonstrations with you, but obviously that's not going to work this term. So let's turn to page 14, please, in the workbook. And at the top of the page, I think we had already filled in the pre-lecture video, the various conversion factors. So you can use these numbers and ratios just to convert atmospheres to PSI, etc., etc. We'll do an example of that a little later on in this presentation. Let's just pause and fill in at the bottom of the page, where does the air pressure at the surface of the Earth come from? So here's a little graphic of a guy, and there's a layer of air. And so what is pressurizing that air? Well, that air that we breathe, of course, is, if I can draw this over there, no, probably won't, is just the very bottom of a column of gases that extends up, say about 50 or 100 kilometers. And so this air that we're breathing at the surface of the Earth is compressed by the weight of the air above it. So we're kind of at the bottom of a sea of air, is one rather poetic way of putting it. So to summarize, here's the text. So the air that we breathe is compressed by the weight of a column of atmosphere. It's, 50 to 100 kilometers high, depending on where you want to call the edge of the atmosphere. The edge of space is at around 50 kilometers, but there's still some gases up to 100. So we'll give you a sec to jot that down on page 14. And so that's where we get the 101,325 from. It's the weight of all that air up above us. Okay, so hopefully you got that down. Let's move on and do on page 17, example 2. Is that it right there? Yes, that's it right there. Okay, so a student sucks on a plastic water bottle and reduces the pressure inside the bottle. Well, of course, we still have pressure outside the bottle, atmospheric pressure. So here's a look at the bottle. Okay, some artist's conception. And so inside, we've got 100 kPa. Outside, of course, we've still got atmospheric, the 101,325 pascals. Let's use consistent units. 100 kPa would be 100,000 pascals. So we see there's less pressure inside the bottle. Consequently, the greater pressure on the outside means there's going to be, okay, so there's going to be a force here from the gases on the inside pushing on the inside surface. There's going to be a greater force from atmospheric pressure pushing on the outside. So those are opposing, and so we're going to find the net or resultant force. How will we do that? Well, we know that a pressure is a ratio, it's a force distributed over an area. So if we want a force, we just cross-multiply the area, it's pressure times area. Now, we don't want to find the force on the inside or the force on the outside. We want the resultant of those two. So we're going to actually take the net pressure and multiply by the area. Now, what is the area? Well, it's given as 600 square centimeters. Now, we have to be really good at our unit conversions at this point. We need to convert to meters, but you see, we're going to divide by 100 not once, but twice in order to convert square centimeters to square meters. So this is not 6, it's actually 0.06 square meters. All right, so we just take the net pressure. The one outside is larger. And you can see I'm running out of room there, so that's the thing I can do here. And that'll be in Pascal units, and a Pascal number is Newton of force per square meter of area. And then we'll just multiply by the 0.06 square meters, and then we'll find the force on the bottle. Now, in terms of the units, notice the square meters cancel out, and so we end up with Newton units, so that's good. And all right, let's quickly do this here. See what number we get. So it's 0.06 times, qu'est-ce qui s'est passé là? 0.06 multiplied by 1325 pascals is 79.5 newtons. There we go. And then this is actually an inwards force. So depending on how strong the plastic is, it may buckle it and cause it to crumble. Okay, so there's a typical pressure example. And so the next thing to do is now to turn to page 20, where there's an example for you to try. So it's example 5, I believe. My numbering isn't always perfect. Let me just check. Yes, it is numbered 5. So pause the video and then give this one a try, okay? Okay, so now I'm going to present the solution to this example. So hopefully you paused the video and gave it a try. There's the answer, by the way, 11.55 centimeters. So hopefully you got that. Let's have a look at the solution. Now, pressure is force over an area. We're asked to find the radius. The way we're going to do that is to actually find the cross-sectional area over here, which is just going to be a circle. Right? Because if these things are hydraulic cylinders, and if we draw a picture of it, it's like that, right? So that's the piston that's pushing up on the car. So the area here is pi r squared. Okay, so we're going to use the pressure ratio to get the area, and then we should be able to find the radius. Oh, so I did the algebra here. Okay, so yeah, the area is pi r squared. So then solving that for radius, you get this expression. And the trick here is to get the right area, you actually have to use the net pressure, just like the example we just did with the water bottle, because yes, the pressure of the hydraulic fluid is 3.3 atmospheres, but of course there's 1 atmosphere of air pressure on the outside here, pushing down on the piston. So the net pressure will actually be 2.3 atmospheres. Now we need to convert that to pascals. We know an atmosphere is 101.325 pascals. And so we use this ratio. Atmospheres will cancel. This will convert to pascals. And then the force in question is just the weight of the car, which is given as 9,800 newtons. So putting those two in, we can calculate the area, and then put the area in there, and then calculate the radius. So with those hints, hopefully you're able to work back and get the answer of 11.55 centimeters. If you're still not getting it, then just fire me a message, and we'll go through it, by our video chat. So I'll just pause there for you to finish writing that down. And then just a comment then. So this is going to be on page 21. Just a definition, because we've seen that a couple of times where we had to subtract to find a net pressure. There's actually a term for this. So switching to page 21, it's a gauge pressure. Now, if you're actually measuring pressure using a pressure gauge, what you measure isn't the actual pressure, but instead it's the difference between the actual and the atmospheric. So here's an example of say, a tire pressure gauge for measuring the pressure in your car or bicycle tires. One side is open to the atmosphere, so there's pressure P naught on this side. The other side, well, this is where you let the gas in that you're trying to measure, so that's P. And so your device actually measures the difference between those two. And all pressure gauges are this way, because they're all exposed to atmospheric on one side. So what you measure we'll call the gauge pressure, and it's the difference between the actual and the atmospheric pressure. So that's terminology that will come up a few times for us. So where we're at so far then is we've done a problem with the pressure ratio. You've tried one, I've shown you the answer, and then we've defined this concept known as gauge pressure. There was one more concept in this section, today's class rather, which is the variation of pressure with depth. Let's do an example of that now together. And this is on page 24, example 8. Now after we've done this one, you guys should be in a position to go and try the extra practice exercises on your own. And we'll touch base with those. Maybe we'll have try and have a meeting either at the beginning of class or between now and next class, just to check those. Because the plan, again, is to do the extra practice in class. We just got defeated by technology today. Okay, so here's example 8. I've added in a couple of graphics. So we've got the giraffe, and its neck is 3 meters long. And we just want to know what pressure do we need in the heart to pump blood up to the top. Now, we're told to assume that the blood reaches atmospheric pressure, so up here at the top is atmospheric pressure, and we just want to know what the pressure is down here. Now, we will use the concept of variation of pressure with depth. That says the pressure at depth, and we can kind of think of this blood vessel as being like a column of blood, so we are getting deeper and deeper in that blood column. So it's the pressure at the top plus the extra pressure due to the weight of, in this case, the blood. So we've got 101,325 up here at the brain, but then because this blood vessel is all full of blood, there's going to be some extra weight, some extra pressure here in the heart. Now we've got to check our units, so we're going to use Pascal units, 101,325 pascals, or newtons per square meter. So rho is the density of the fluid, which is blood, and the density is given. So there's the density ratio for blood. G is the gravity field, 9.8 newtons of force per every kilogram of matter. And D is the depth, or in this case, yes, how deep are we in the blood column? It's 3 meters deep. And so now, we just work that out quickly. Let's see what we get. Okay, so there it was 132, 195, is that right? Yeah, okay, 132, 195. Now, in terms of units, if we look over here, you'll see the kilograms cancel, and then one of the newtons cancels. So this is a newton per meter squared, so that is a pascal. So we have pascals and pascals, so we can just add them together to get the total blood pressure. So that's how much pressure we need to have in the giraffe's heart to push blood up that high. Okay, part B of the example says, okay, you've got the pressure, express that as a gauge pressure. What does that mean? Well, a gauge pressure, as we just saw, is the difference between the actual and atmospheric. So that's just the 101, sorry. flub, 132, 195, minus the 101, 325, and this will be in Pascal units. And there it is, 38.7. Okay, and we're asked finally to express this in different units. So we've got that gauge pressure in Pascal units. We want to convert it to units of millimeters of mercury, which are the units of blood pressure. So we're going to use atmospheric pressure as the sort of reference point for that conversion. And then we're going to convert it from pascals, so pascals will cancel, and then convert it to millimeters of mercury. Now, 1 atmosphere of pressure is 760 millimeters of mercury, and it's 101,325 pascals. So in this way, this ratio is 1, because this number and this number are the same. But multiplying by 1, we've sort of set it up so that we can actually convert to the units that we want. This is a sort of standard way of converting units. It's used quite a bit in chemistry. So let's see what we've got here. Uh-oh, that's not going to work. 5, and we multiply by 760, and we get 231.5. Now that's off your screen, but it's on mine. And there, we've converted to the required units. And so that finishes my presentation for today. And what we would do next, if we were together, is I would say, okay, now it's time to work on those extra practice problems, the 1, 4, 9, 10, 15. And hopefully by our next class, things will go better, and we'll actually have time to do that. Because some of these are a little tricky, and so it's helpful if I can kind of drift around and offer you some advice a little bit, and you can ask questions about them. That will be our eventual destination, but for today, just give them a try on your own, and I guess, yeah, we'll find some time, probably at the beginning of next class, just to go through them together. So, yes, work on those problems. You can also have a look at the first assignment, and then I'll see you next class. Remember, there's a pre-lecture video to watch and notes to take before you come. Thanks for your understanding.